time for convolutions. This is a really important technique that usually we use to lead us into a project where we track the position and movement of a mouse in a video of an open field test. We may or may not do this exact version of the project this year, but we're definitely going to do something with it because they're so cool and you can do so much with them. So here's the idea of a convolution filter. It is a single algorithm that can be used for lots and lots of different effects that are useful in other algorithms. So with the same algorithm, you can lighten or darken, you can pixelate, you can do different kinds of blurs like Gaussian blur, you can sharpen, you can do edge detection, you can emboss, all kinds of things. So how does it work? The big idea is you're going to loop over all the interior pixels of an image, and you're going to replace each pixel with a weighted average of the surrounding pixels. And there's a couple of different ways that you typically see this show up when people talk about it, and I'll try and show you all the different ways. So here's the idea. Let's say we've got an image. This center red square is the pixel that we're going to replace. So we're imagining we've been looping over this image already. What are we going to replace this 8 with? What we're going to do is we're going to find right now just the average of all the values inside the dashed blue square. So we'll add up 763, 782, 168. We'll divide by 9. That gives us the average, and we'll replace this 8 with that new value. So there we go. The new value is 5.33. Obviously, we can't have a grayscale value with decimals in it, so we'll truncate it just to 5. The other important note is if you were going to actually change the image as you were looping over it, that would affect the calculation for the next pixel over, because this changed pixel would now become part of the average for the pixel next to it. So rather than change the original pixel, you're actually going to write to a different image that would be an output pixel. Okay, so let's switch up how we're thinking about it a little bit. Instead of thinking you can add up all the values and divide by 9, that's the same thing as saying, what if you multiply each value by 1/9? So you can think about this as we're going to give each of these pixels the same weight. So let's give them all a weight of 1. So I'll take 7 and multiply it by 1. I'll add that to 6 multiplied by 1, and so on. And then at the end, I'll divide by 9. Hopefully you'll see that you'd get the same result if instead of that, you just multiplied each value by 1/9 and added them all up. So depending on where you look this up, and if you look up matrix convolution, you'll see a whole lot of different resources about this. Sometimes people will show you a kernel, this thing's called the kernel, where all the different weight values are integers. And sometimes they'll show you a kernel where all the different weight values are proportions for how much of the total weight of 1 should get assigned to each pixel. So I'll kind of show you both ways. For our in-class implementation, we're going to be using a version where the numbers here give the relative weights, and we'll end up dividing by the total weight of the entire kernel. If this is confusing, hold on for just a second, and I think it'll all become clear in just a second. So, reviewing vocabulary. This 3x3 grid of numbers is called the kernel. All the numbers inside are called weights. And what they give is they give the relative weight or the relative importance of each of the surrounding pixel values when you do the weighted average. So, let's keep going. Depending on how your kernel is shown, either you'll add up all the numbers and they'll add to 1, in which case you don't need to do anything else. Sometimes they'll all add up to 0, in which case you don't need to do anything else. Sometimes you might see a kernel like this. So what this would mean is, let's take 7, multiply it by 3, 6, multiply it by 1, 3, multiply it by 3, and so on. But then at the end, you'd have to divide by the total weight of the entire kernel. So take a minute, add these up, decide what you get when you add them all up. That's the weight of the kernel. So let's see, it looks like 5, 5, 5, that's 15. Here I'm seeing 3, 3, 3, 3, so that's 12. 15 and 12 is 27. This is 28, 29, and 30. So I think there's a total weight here of 30. So if this was the kernel that we were using for our weighted average, what this means is we're giving the pixel values right in the middle here, 7, 8, and 2. We're giving these the most weight because they're getting counted 5 times. this pixel directly above is getting the least weight. It's got a weight of 1. And the 4 corner pixels are all receiving an equal weight of 3. That's what we mean when we say weighted average. So the way we'd calculate the output pixel is what I just did. You multiply each pixel by its corresponding weight, add up all those pairs, but then divide by the total weight of the kernel. And remember, you only do that when the kernel doesn't, when all the total weight of the kernel doesn't equal 1 and doesn't equal 0. All right. So one more example, just in case this isn't clear yet. Here's a kernel that performs an emboss operation. So you see most of the pixels get a weight of 0, but then the upper left and lower right hand pixels get opposite weights. A negative weight means that we're going to sort of count lighter values the opposite of what they would ordinarily count as in an average. So how do you compute the output pixel? We're going to multiply corresponding elements again. If the input pixel is black, we multiply it by 4, but that's still 0. 0 times 0 is 0. 0 times 0 is 0. So we sort of go over it. 1 times 0 is 0. So the only pixel that actually has any influence here is this lower right-hand pixel, which is getting multiplied by -4. And when I add these all up, I get an overall value of -8. And that's what the central pixel gets replaced by. Remember, it gets replaced in an entirely new image out here. So again, we loop over the square region, multiply the corresponding values, replace the center pixel. In this example, you might be wondering, well, what does -8 really mean as a color value? If you get a value that's below 0, replace it with 0. If you get a value that's above 255, replace it with 255. That's called clipping. All right, so you can see it in action by going to this website. I'm going to actually just show you a little bit what it looks like. So let's scroll down a little bit here. This is a really nice kind of animation that shows you what's happening. So you can see on the left-hand side, we've got the 3x3 region. And then you can see in the center there, it's actually telling us the grayscale values for all the pixels. And it's also showing us what each pixel is getting multiplied by. Here's the kernel that we're using. This is a sharpening kernel. So we've got weights of 0, 0, 0, 0 in the corners, -1s on the sides, and 5 in the middle. And so you can see each of the grayscale values is getting multiplied by that corresponding weight. And then the result, you can see in the middle there, is 110. And that's the color of the red square on the right-hand side. That's the output. So you can see the input image, you can see the calculation, and the output image. And if you want to, you can play around with different kernels. So that's sharpen. Here's blur. Here's bottom Sobel, which we'll talk about probably next week. Sharpen. Oh, we did sharpen. Well, so identity just means you don't do any change. So you can sort of play with that as a way of understanding how the algorithm works. All right, question. So what happens to the border pixels? Because remember, you can only replace a pixel if you can loop over the 3x3 region surrounding it. Border pixels, you can't do that. I think what we should really do is just leave those border pixels untouched. There are alternative options. You could just choose to assign the border pixels to be black or white. You could choose to give them the same value as their neighboring pixel. You could assign them using wrapping. So if I'm trying to replace this border pixel, I'll count the pixel on the other end as being part of the weighted average of this pixel. There's other things that you can do also, but I think for our algorithms, let's just leave them untouched. So like I said, there's lots of applications here. There's applications in medical imaging. You can use this the same matrix convolution to do edge detection if you want to like really bring out the contours of something, such as a license plate, if you were going to perform optical character recognition to try and identify what does the license plate actually say. Let's skip that one. So today, so that was about 10 minutes. So today you got 20 more minutes to try and actually implement a 3x3 convolution filter according to this algorithm that we just described. If you want to, you can jump straight to an n by n convolution. So instead of looping over a 3x3 area centered on a pixel, you'd loop over an n by n area centered over a pixel, assuming that n is odd. We're only going to work with odd-sized kernels. Going into next week, I'm going to describe several different types of edge detection that kind of get increasingly fancy, and that's another thing that you can try. As a last note, let's just think through the algorithm for a second. So if R and C are pointing here at this location, how would I loop through a 3x3 region with RC as the upper left? Think about kind of what you'd fill in here. Hopefully, you said something like this. I is less than R plus 3, J is less than C plus 3. Pixels, I'm imagining, is my source image pixels. So let's think about it a different way before we get to how to multiply by the corresponding weights. What if instead of this, I want R and C to be pointing at the middle, and I want to loop over the 3x3 region where RC is at the middle? In this case, you can loop from R minus 1 up to R plus 1. So it just depends on kind of what R and C are going to describe. All right, so let's go back to the first way. So now R and C describes the upper left-hand corner. Remember, I can't actually use those same indices in my 3x3 kernel. Because remember, the upper left-hand corner of your kernel is 0, 0. It's a completely separate two-dimensional array whose indices only go from 0 to 2. So think about how you'd need to adjust I and J if I and J are describing the indices in your entire image in order to describe the kernel indices itself. So this is very similar to like both of the filters that we've done over the last week where you need to adjust indices. So if we subtract R and C, think about what that's going to be when you loop through it the first time. I is initialized to R, J is initialized to C. So we're getting the source pixel out of RC, but then we're accessing the kernel weight that's at R minus R would be 0, and J minus C would be 0. So we're actually accessing 0, 0. And then as R and C, then as I and J change, out of the kernel, we're only getting the relative differences from 0, 0 as I and J are changing. Okay, check out the assignment for details. Good luck.